This lecture is from Chapter 1 of your textbook, and the topics it's going to cover are the metric system, the difference between precision and accuracy, how to deal with significant figures, and probably the most important topic is, in chemistry, unit conversions using a process called dimensional analysis. I'm hopeful that y'all have been exposed or learned this already, so this may be a review, but it's an important review. So let's go over the metric system units first that are used in all of science. It's also called the System International SI system. But length will be meters, abbreviated little m, lowercase m. Mass is in terms of kilograms. Actually, most of the time we'll just use grams. Time, the accepted SI unit is seconds. Temperature is Kelvin. However, many scientists will use degrees Celsius also. And later on the semester, we'll talk about what a mole is. And that's the quantity in the metric system. There are several metric prefixes that you'll have to commit to memory, including mega, kilo, centi, milli, micro, and nano. And how you interpret or deal with this chart is, for example, if you were talking about a megagram, okay? So we'll say megagram. It would be abbreviated capital M for the mega and little g for the gram. You got to be really careful with metric prefixes, whether it's capital or lowercase, because little lowercase mg is milligram, okay, right here. Anyway, so what this is telling you is that a megagram is 1,000 times the size of 1 gram of the base unit. Not 1,000, a million, sorry. Okay, so a megagram is whatever the base unit is, whether it's gram or liter, times a million. And then, for example, a milligram is 0.001 times the base unit, which is gram. Okay, so a milligram is 0.001 gram. So anyway, that conversion chart, you may want to copy that down on a note card or something and have it handy so you can commit it to memory. All right, temperature scales. Fahrenheit is what we use because we like to be different than the rest of the world, apparently. So, but scientists will use Kelvin or Celsius. So I'm not going to ask you to do any conversions from Fahrenheit to anything else. So your textbook has a couple of them, so don't worry about that. But I will ask you routinely to convert back and forth between Celsius and Kelvin. And a couple things I want to point out. One, here's a formula you need to know. And when I was taking courses like this, I used to have a section of my notebook or a few pieces of paper or something that were separate where I would write down all the formulas. And then when it came time for a test, I would have all the formulas for that unit in one place. And then when it came time for the final, I'd have all the important formulas for the entire semester. So this is an important one, to be able to convert from Celsius to Kelvin or vice versa. So a couple things I want to tell you just to kind of help you remember. The Kelvin value in temperature is always going to be larger than the Celsius value. So because you're adding something to it, right? And I don't really care. You can just add 273. I don't care about the 0.15. But the one mistake I see students doing on these conversions is they get mixed up what to add to what or subtract. So just remember the Kelvin value should always be larger. And then the other thing I want to point out to you, which is kind of interesting, is that the change in degrees Celsius is the same thing as the change in Kelvin. So let me explain what I mean. So the absolute values are different. So 0 degrees Celsius equals 273 Kelvin. Okay, you look at this formula here. But let's say that we took the difference between the boiling point of water and the freezing point of water, and I asked you what that difference is. It wouldn't matter. So if you're talking about any delta value, any difference, it's going to be the same for Celsius and Kelvin. Not true for Fahrenheit, though. So the change between the boiling point and the melting point or freezing point, they're the same, for water is 100 degrees Celsius, but look at this. It's also 100 Kelvin. So that'll help you on later in the semester. Anytime there's a formula that has delta or the change in temperature, don't go converting everything from one to the other. You're going to get the same answer. All right, so here's one just to give you a quick try. How do you convert from 2.73 Kelvin? What is that in Celsius? So when I have these you try questions, I suggest to you to put the video on pause, work it out yourself. I'm here to tell you right now, the key to doing well in chemistry, no matter how lazy or tired you feel, is to force yourself to do every single problem I give to you. That's the way to success. You can't memorize and succeed in chemistry. You actually have to put pen to paper and do work. So go ahead, put the video on pause for a minute and work that out. And always get in the habit of always showing your work. So I start all of my problems by writing down the appropriate formula. And that is Kelvin is degrees Celsius plus 273.15. All right, so we're just going to take the, I'm going to plug in 2.73 equals degrees Celsius plus 273. And then, of course, just rearrange the equation. I'm going to subtract 273.15 from both sides. Okay, and there is your answer. Okay, 2.73 Kelvin is minus 270.42 Celsius. So I don't know if you've ever heard of absolute zero, but the whole reason the Kelvin scale was developed is so that we would have an absolute zero. What the heck is that? Okay, first of all, its value is not okay, it's 0 Kelvin. And that theoretically is when all motion of an object ceases. In other words, it's impossible to get any colder than that. And scientists believe that it's theoretically impossible to reach that. They've gotten really, really, really close to that value, like infinitely close, but not exactly on it. All right, so now we're going to kind of ease our way into using the metrics and talking about the uncertainty in every measurement. So in lab, this is going to be particularly important in lab. We will introduce it in lecture, but it's critical in lab. I've unfortunately actually seen students fail a few lab reports for not paying attention to the level of uncertainty in a measurement, which brings us to significant figures. So as you know, anytime you measure, let's say you get out your tape measure and you measure the distance of something, well, you're going to get a slightly different value than somebody else who's going to measure it. There are all sorts of potential errors. Maybe you're not holding the tape measure completely straight. Maybe you estimated the edge of the object you're measuring against tape measure. You estimate a little bit different than somebody else did. So there is always uncertainty in every single measurement. And so the number that you record and use in a measurement must be representative of how certain you are. And that depends on in part on the equipment you're using for that measurement. So the more precise the equipment is, the more significant figures that you're going to have, and the more certain you're going to be about the measurement. So let's say you measured, here you're measuring mass, obviously grams, and you measured it 5 times, and these are the various values you got. I would call this quite precise, okay? This, between the 5 measurements, it's only varying in the 1/10,000th place, so that's quite precise. Alrighty, so as I said, the degree of precision or the degree of certainty in a measurement depends on the equipment you use. So if somebody said go measure out 10 milliliters of water and they wanted it precisely measured, which one of these pieces of equipment would you think would give you a more precise or more reliable measurement? Hopefully you would pick the burette. And so what the precision or certainty depends on is the size of the increments, okay? The smaller the increments are, the more precise the measurement and the more significant figures you're going to have. So check out the beaker. It only has increments every 10 milliliters. So if you were asked to measure 10 milliliters on the beaker, you'd probably get pretty close, but yeah, not great. So hopefully you'd get between, you wouldn't get way off. You'd get close to 10, okay? Now, graduated cylinder, it's got increments every, this one has it every 2 mils. Interesting. Usually they're every 1 mil. And so that's going to be a little more precise. And what that means is if you measure 10 milliliters out several times, you'd get more unified values that are closer to each other. That's what it means to be more precise. It's repeatable. And then a burette has demarcations every 0.1 milliliter, okay? So the burette's going to give you precision to the 1/100th place. So you'll learn, I'll walk you through how to report with the correct number of sig figs, but for now I just want you to know the smaller the increment, the more precise the measurement, and the more sig figs the value needs to be reported in. All right, so you will probably want to write down these instructions, unless by some freak chance you know them already, but which I kind of doubt in my experience, okay? So you're in a lab, let's say, and I think your first lab has to do with sig figs, so I would jot this down or listen to it a couple times if you need to. Let's measure the volume of the liquid that's in this beaker, and let's measure it with the correct number of sig figs. So we know for sure that the volume of liquid in this beaker is between 20 and 30. It's not less than 20, it's not more than 30. But this digit here, we don't know for sure. And so that is our estimated digit. Every single measurement, the far right digit on the digit on the right that you're uncertain of, that is always an estimation, okay? So now we have to eyeball it and estimate what that actual volume is. And your estimate's going to be a little bit different than mine, which will be a little bit different than your lab mate. So I would estimate that as 28 milliliters. Okay, you might say 27 or 29. It's going to be a little different. So the last digit of any measurement is going to be an estimation. All right, let's do it again. Let's do it for the graduated cylinder, and then I want you to try to do it on your own for the burette. So the graduated cylinder, this volume here, what do we know for certain? We know for certain that it's in between 28 and 29, okay? So we know that the first digit is a 2. We know the second digit's an 8, right? Because it's not greater than 29, okay? So we have to add another digit that is an estimate between the smallest increments, okay? So it's going to be 28 point something. So let's look and estimate. So I say it's 28.2 milliliters, okay? But somebody else might say 0.1 or 0.3. That's fine, okay? The last digit is an estimate. So now I want you to take a minute, and I would recommend shutting off the video and look at this burette and estimate with the correct number of digits, significant digits, what you think that volume is. So these are marked every 0.1. So 28.1, 0.2, 0.3, and 0.4. So we know that burette is between 28.3 and 28.4. Yeah, okay. So the bottom line is we know it's not exactly 28.4. Okay, we know the 2 is for certain, the 8 is for certain, and this 3 is for certain. Okay, it's going to be past the 28.3 here. So we need to add another digit that is an estimate. So now go back to the image and estimate. By the way, I have 3 dogs, if you didn't listen to my welcome video, and so you will suddenly hear noises from them in the background. I just didn't want anyone to be startled. So let's say I'm going to call that 28.31 milliliters. Alrighty. Okie doke. So that is really, really important for lab. All right, so now let's say you have these measurements, have the correct number of sig figs, and you're expected to plug them into some formulas and do calculations with them. There are a series of rules when you're dealing with significant figures and measurements, and you just need to commit these rules to memory. So the first thing you need to do is determine how many significant figures are in a value. So if you're not talking about measurements, you don't care about sig figs. They're meaningless, okay? So this is only measured values. So if there are no zeros, it's zeros that get confusing, okay? So if there are no zeros, every digit is significant, okay? Every digit is meaningful. That's what we mean with significant. So 1, 2, 3, 4, 1,234. That is 4 significant figures. Now, zeros are the iffy part. So let's do the easy ones first. If there's a 0 between 2 non-zero numbers, okay, so if it's a 0 that's trapped, it is significant, which means it's important. It's an important number in the measurement. So this has 4 sig figs. Okay, here we go. Zeros at the beginning of a value. So I used to call these leading zeros, and then students would get mixed up. What do you mean by leading? So any zeros that show up at the beginning of a number are not significant. They're not part of the measurement. They don't depend on the precision of the measuring device. They're there simply as placeholders, so they don't represent precision. All right. So this number, for example, only has 3 sig figs, the 5, 9, and 2. Zeros at the end of a number are the ones that are iffy and the ones you have to pay attention, okay? So if there are zeros at the end of a number, they might be significant, but they might not be significant. So the bottom line is, if zeros at the end of a number, if there is a decimal any place in the number, at the beginning, at the end, in the middle, any place, if there's a decimal, then these trailing zeros or zeros at the end of a number are in fact significant. So there is a decimal here, so it has 1, 2, 3 sig figs. Okay, here's another example. 0.300, the leading zero, the one in the beginning, never counts. And there is a decimal in the number, so the ones at the end do count. All right, so that has 3 sig figs. Now, scientific notation, the exponent, the times 10 and the exponent, don't factor into the sig fig, okay? That's nothing to do with the measurement. It represents the magnitude of the number. You can't just leave it out, but it doesn't tell us anything about the precision of a measurement. All right, so now let's talk about trailing zeros. Zeros at the end of a number, and there's no decimal point in the number. If there is no decimal point, zeros at the end of a number are not significant. Now, that doesn't mean you can leave them out. They tell us important information about the magnitude of a number. They just don't give us information about the reliability or precision. So, whoever did this measurement, 96,500, had an instrument that allowed them to be certain of the 10,000s place, the thousands place, and the hundreds place. But the equipment was not sensitive enough, not precise enough to tell them in the tens place and one place what the value is. So that's all that means. All right, so you need to memorize those rules. You may want to jot those down. Now, calculations with sig figs: addition, subtraction, multiplication, division. Addition and subtraction is what students tend to mess up on if they're going to mess up. So try to pay attention if you've kind of been spacing out of me, okay? So if you are adding and subtracting, it's easiest to line them up vertically, the numbers that you're adding or subtracting, because you have to express the answer with the correct number of sig figs. If you just plug these values into your calculator, you're going to get this entire value, 5.4125. But if you report it as that, you're going to lose points, okay? Because the number of significant figures in the answer has to reflect the precision of the numbers that went into that answer. So if you're adding and subtracting, what's important are the number of decimal places. I'm going to say that again. When you're adding and subtracting significant figures, what's important are the number of decimal places. So this top number has 3 decimal places, 3 places to the right of the decimal. The second number has 2 places to the right of the decimal. It doesn't matter if they're 0 or non-zero. You're just literally counting places to the right of the decimal. The bottom number has 4. Now, the number of significant figures, or the precision of the answer, is going to depend on the value with the least precision. And in adding and subtracting, again, it's the number of decimal places to the right of the decimal. That sounded weird. Anyway, so the one with the least is this middle number, 0.07. It only has 2 digits to the right of the decimal. What that tells you then is your answer can have no more than 2 digits to the right of the decimal. All right, so the correct answer here is 5.41. The same rules apply with subtraction. Okay, this first number only has 1 digit to the right of the decimal. The second number has 3 digits to the right of the decimal. You take the smaller number of digits to the right of the decimal, and that determines how your answer must be expressed. So your calculator is going to give you 5.679, but your answer can only have 1 digit to the right of the decimal. Now, this is really important about rounding, okay? You can't just, okay, I'm only going to take these 2 digits and not pay attention to anything afterwards, because then you'd get it wrong also. The correct answer is not 5.6, because you have to follow rounding rules. So once you determine the number of sig figs that you have to round. And so the rules for rounding is the first number that's dropped, if it is 5 or greater, you're going to round your value up. So it goes to 5.7. If the first digit you drop, so in this first one, the first digit we dropped was a 2. So if the first digit dropped is less than 5, so if it's 0, 1, 2, 3, 4, you're going to keep that last digit the value that it is. All right, multiplication division is easier. Multiplication and division with sig figs, you just count the total number of sig figs in each of the factors. So the number of sig figs in this is 4. number of sig figs in the next number is 5, and the number of sig figs in the third number is 2. The number of sig figs in the answer is always determined by the least precise number that went into it. So the least precise number had 2 sig figs, which means our answer can only have 2 sig figs. So 6.7. Now, before you just write 6.7, check out the first digit that's dropped, in this case a 2. If that were a 5 or greater, it would have to be round up to 6.8, but it's not. All right, same with dividing. It has 5 sig figs, this has 3 sig figs. Your answer can only have 3 sig figs. So 1, 2, 3. You're going to cut it off, but you're going to check the first digit drop to make sure it's not a 5 or greater. It's not, so we don't round up. We just keep it 0.626. Alrighty, so one more thing before we do some sample calculating with sig figs are what we call exact numbers or counting numbers. So there are some numbers that are not measurements, they're just defined as a fact, and when you're dealing with that type of number, it doesn't take part in determining the sig figs for an answer. So for example, a dog usually has exactly 4 legs. So 4, when it's referring to dog's legs, is an exact number. And exact numbers have unlimited number of sig figs. They will never be the limiting consideration when you're doing calculations with sig figs. That's true with any number that can be counted. All right. So I have exactly 10 fingers. I don't have 9.5 fingers. I don't have 10.2 fingers. I have 10. And so 10 fingers is an exact number. It doesn't have 1 sig fig. It doesn't have 2 sig figs. You don't even talk about sig figs with counting numbers. There are also some conversion factors that are just defined, and therefore, again, you don't take into consideration sig figs. So metric conversions are all just definitions. There are exactly 100 centimeters in a meter, and so if you were doing this calculation, you would say, okay, 3.63 has 3 sig figs, and you wouldn't even pay attention to the number of sig figs in this conversion factor. Okay, you wouldn't say, oh, it's got 1 because there's no decimal. No, you just ignore it as far as the sig figs because it's an exact number. And so when you do the calculation, 3.63 times 100, 363 needs to have 3 sig figs, just like the value you started with. All right, so we already talked about rounding. I probably should have moved this slide back a couple places. But what I always tell students is go ahead and plug everything into your calculator, and don't round. Like if it's a multi-step calculation, don't round it until you're completely done with all the steps, because you're going to get an artificially truncated value that'll likely be wrong. So for example, if you're doing this complete calculation, don't do 6.78 times 5.903 and then round it and count sig figs. Just do the whole thing, okay? So what's in the parentheses first, right? You're going to subtract, then you're going to multiply it by these 2 numbers, and then you're going to get an answer in your calculator, okay? Now you have to go back and figure out how many sig figs that answer should be reported with. So let's look back. And I know this is in your first lab in 1211, so try to pay attention. So first we're subtracting, right? And remember, when you subtract or add, you have to count digits to the right of the decimal. So this first number has 3 digits to the right of the decimal. The second number has 2 digits to the right of the decimal. And so the answer to this subtraction portion can only have 2 digits to the right of the decimal. All right. So if that was the only calculation involved, we would report it as 0.48. But it's not. It's a multi-step calculation, so don't round yet. Just go ahead and write down what your calculator gave you. and we'll round at the end. But we know, make a little mark, what some people do, under the 7, because we know that 7 is the last significant figure. All right, so now that you've done that, all that's left is multiplying. And we know the rules with multiplying or dividing. You count total sig figs, okay? So 6.78 has 3, 5.903 has 4, and this only has 2 sig figs. Remember that 9 is not counting as significant. We're just carrying along to get the most accurate number at the end. So our answer can only have 2 sig figs. So you're going to write down everything your calculator gives you, but then you can only have 2 sig figs. So the 1 and the 9. Check the first drop digit, which is a 1, to make sure you don't have to round up. So your final answer, expressed with the correct number of sig figs, is 19. Alrighty, if you need more practice, just again look at the first round. If you're rounding all these to 2 sig figs, again, you're going to look at the first drop number always. If it's a 5 or greater, it's going to round up. If it's less than a 5, for example here, you're going to just keep the last significant digit what it was. All right, just quick couple slides on density, and I think that's part of your first lab also. Density is basically how much mass you have crammed in a certain volume. So you may remember, it's a good thing to commit to memory in this class, that the density of water is exactly 1 gram per milliliter. What does that mean? That means if we get a milliliter of water and we weigh it, it's going to weigh exactly 1 gram. And so kind of a qualitative way to determine the density of things is put them in a vat of water, right? If they float, there goes that's Amazing Grace starting to whine. If we put them in a vat of water, if they float, they have density less than 1. If they're kind of animated suspension like the banana, they have density very close to water. And if they sink, their density is greater than 1. And so and the particulate images on the left just kind of show you, we'll be doing a lot of particulate models in chemistry, so you can kind of see what the atoms or ions are doing. And so if you have a high density item, it just means all the atoms or the ions or particles are packed very close together. Okay, so that means a relatively small volume is going to weigh a lot. If you have something that's low density, like styrofoam, that means you can have a large volume, but it's not going to weigh very much. And that's because on a particulate level, the particles are not very close together. And so just to remind you of the formula for density, you hopefully have worked with this, but if not, density is mass divided by volume. And so I think you do that in the first lab. I think you're going to measure out a volume and then weigh it and calculate density. But you got to pay attention to all the sig figs. So I have this magic triangle because I have learned that I have had some brilliant chemistry students that just struggle with algebra. That's actually pretty common. And so I try to give you little tools to deal with that. Any formula we deal with, you're going to have to rearrange it. So some people can look at this formula and go, and if I ask you to solve for mass, you're like, okay, yeah, mass is density times volume. But other people are going to get mixed up. And so if you've never used these magic triangles, how you use them is you put whatever is on top in the original formula, like this case, it's mass. That has to go on top in the triangle. It doesn't matter the order of what goes on the bottom, as long as you put everything else on the bottom. And so then what you do, if you need to rearrange the formula, whatever you're trying to solve for, you cover up. So let's say I asked you to solve for volume. So that would mean in this triangle, you cover up, I usually just put my finger over it, but you cover up volume, and what are you left with? That tells you then that volume is mass divided by density. Okay? So again, you don't need that triangle. If you can look at this formula and say, oh yeah, okay, volume is mass divided by density, then you don't need the triangle. But in any case, you're going to have to rearrange this formula to solve for all of the variables. All right, so here is an example I'm going to do with you, for you, and then I've got one that I'm going to ask you to do on your own. All right, so the units for density, I didn't go over on the last page, but they're more commonly grams per milliliter, that's mass per volume, or grams per cubic centimeter. And one other little equivalency that's really handy to know in chemistry, and you may not be aware of it, it's kind of cool. 1 milliliter is exactly the same thing as 1 cubic centimeter, so you can literally just change one unit to the other without doing anything. All right, so here's a question. If the mass of an object is 35 grams and volume is space, volume is how much space something, 7 cubic centimeters of space, what is the density? So again, I always start by writing the formula. Density is mass over volume, and then plug in the values. The mass is 35 grams, and the volume is 7 cubic centimeters. And so if you plug that in your calculator or do it in your head, right, that means that the density is 5 grams per cubic centimeter. And that's exactly, you could express it as 5 grams per milliliter too. Remember I said milliliter and cubic centimeter are the same? Alrighty. So here is a you try question for you to do with density. And so I would recommend at this point turning off the video and trying to work it out on your own. And then turning it back on and I'll work it out for you and you can check your answer. Now, one of the things that I want to say about problem solving is I try to have a combination of very simple, straightforward problems plus some that are more complex so that by the time you get to the homework is assigned, you have a feel for things. But this one in particular is actually asking about 3 different questions in one. So there's several things you need to be aware of. And keep in mind that throughout this Unit 1, you have to express all the answers of every calculation with the correct number of sig figs. So get yourself in the habit of doing that. So as always, I'm going to start by writing the formula. Density is mass over volume. And then I'm going to read the question again. Okay, here is my mass. All right, so 163 grams. And my volume. It gives me 2 volumes. But that is a really common way to determine the volume of an irregularly shaped object. You probably know that if you have something that's in like a cube or a box or something, you can measure the volume with a tape measure, that it's length times width times height, right? And that gives you cubic centimeters or cubic meters. But if you have an irregularly shaped object like a rock, how do you measure the volume of that? So a lot of times people put it in a container of water and then measure how much the volume goes up, okay? And that difference in volume is the volume of the rock. Kind of cool, huh? So that's why you have 2 volume readings. So if you have 2 volume readings, you just want to subtract one from the other. So 58.5 minus 50 gives you 8.5 milliliters, and that is the volume of the rock. So now I'm going to go back and plug that volume, 8.5 milliliters, into the equation for density, and then I'm going to plug that into my calculator, 163 divided by 8.5. And I'm going to write down a whole bunch of extra digits. I always do that, and then I figure out how many sig figs I really need. So since this is division, I need to count total sig figs of each of the factors. So the numerator has 3 sig figs. The denominator has 2 sig figs. So my answer can only have 2 sig figs. So I got to look at the first drop number to see if I need to round it. I don't, because it's less than 5. So my final answer is going to be 19. The units are gram per milliliter. Then the question asks me if it's gold. So I'm going to look up at the density of gold. And it is, in fact, 19 grams per milliliter. So my answer would be yes, it's likely gold. All right, so we're on the final stretch of this PowerPoint, and the remaining slides are going to be a method called dimensional analysis. It's also called unit cancellation, and we do that a ton in chemistry. So, but I will tell you, even though a lot of students complain about it, if you pay attention to the method and you have enough discipline to kind of force yourself to go through it, you can do the most difficult problems without even thinking about what you're doing. All right, so here's the basic procedure of a dimensional analysis. Anytime you are given units, let's say density in grams per milliliter, and somebody says, well, I want to know what that is in pounds per cubic meter. So that's a unit conversion, okay? So here's the method you would need to do. So you start, there's always a given unit, and that's stated in the question itself. So you go to the question, and let's say it was grams per milliliter. And let's say that they asked you to convert that to pounds per milliliter. Okay, that would be a unit conversion. So you start with what's given in the, whoops, it's not 5, sorry. So you start with what's given in the problem with the units. And then you're going to need a conversion factor. You're going to need some conversion factor. Now, milliliters is staying the same in this example, but we need a conversion factor that'll take us from grams to pounds. And so, hopefully, if they're nice, I would always give you the conversion factor, unless it's so simple you should know it, but most of them I'll give you. So, in this case, there are 454 grams per pound. Okay. So you're going to use that conversion factor to do the reaction, or to do the calculation, but you have to arrange that conversion factor in such a way that units cancel. So let me show you what I mean. 5 grams per milliliter. Now you remember the rules of algebra that things on a diagonal cancel. So you want to arrange the conversion factor so that the units you want to cancel are in the denominator. Okay. So grams per pound. So you want pound on top. Whatever unit you're trying to get to goes on top. The units when you cancel go on the bottom. So in this case, that's 454 goes with the grams, not the pounds. Okay, so that's a denominator. So be very careful of the units. That is the most important part of dimensional analysis, is to line up the units of your given information and your conversion factor so that they cancel out. So this is actually a division. It's 5 grams per milliliter divided by 454, okay? And that will give you, when you plug that in, pounds per milliliter. All right, let's do some of them. Here's some common conversion factors. If you get any problem and the problem doesn't give you a conversion factor, just look it up on the internet. They're really, really, really easy to find. And remember then, okay, so this is how conversion factors are given. They're given as an equivalency. 1 inch equals 2.54 centimeters. When you use it in dimensional analysis, you've got to convert that equivalency to a ratio. So there's 2 ways to do it. You could either say 1 inch on top and 2.54 centimeters in the bottom, or you could put 2.54 centimeters on top and 1 inch on the bottom. And you can easily use that conversion factor in either way. It depends on the units of the given information. So whatever units we have in the denominator, they should match the identical units of the given information, so they cancel out. All right, so here's an example. This problem, I should have written it up here. If you have 16,100 kilograms of something, how many liters is that? So that's typical dimensional analysis. You're going to start with the given information, 16,100 kilograms. You need a conversion factor between kilograms and liters. And in this case, they gave it to you. They said there's 0.8 kilograms. So it would be written like this, 0.80 kilograms equals 1 liter. And you would arrange it so the units of the given information are on the diagonal, and those units are going to cancel out. And so the math here is then 16,100 times 1 divided by 0.8. And so your calculator is going to give you 20,100, but now you have to think about the number of significant figures. So the first number has 3 sig figs, right? Trailing zeros at the end of a number are not significant unless there's a decimal point, and there's not. And so 1 liter, 0.8 kilograms in 1 liter. That 1 liter only has 1 sig fig, unfortunately. So that tells you your answer can only have 1 sig fig. So the 2 is the only sig fig in this answer. All right, so it gets a little bit trickier when you have squares or cubic units. And so I wanted to do a specific example showing you how to handle those. So if you have units of, let's say, centimeters squared, and you want to convert that to inches squared, okay, you have to do that conversion 2 times. Whatever your exponent is, that's how many times you need to do it. All right, so let me show you what I mean. Let's say that we have 5 square centimeters of something, and I want to know how many inches. So my conversion between centimeters and inches is here, and the centimeters needs to be in the denominator, so I'm going to put 2.54 centimeters down here, 1 inch here. This only centimeters squared means what? It means centimeters times centimeters. There's 2, right? So this centimeter only cancels out one of them. I have got to do it again. So how you get your answer, it's going to be 5 times 1 times 1, so pretty much everything in the numerator, okay, divided by 2.54 times 2.54. All right. So let's do a sample of those. How many cubic meters is 1,500 cubic centimeters? What happened to my little multiplication? Start with the given information, 1,500 cubic centimeters. Now, there are 100 centimeters in 1 meter. That is such a simple conversion. Those simple conversions you need to commit to memory, okay? So simple metric conversions. Now, another thing I want to mention to you is that this is a defined conversion. Somebody just randomly said, okay, we're going to call 100 centimeters exactly 1 meter. So that means that there are unlimited sig figs. So you do not take exact numbers or define conversion into account when you're determining sig figs. All right, so anyway, this is centimeters cubed. So we have to divide by centimeters 3 times. It should all be times, okay? And then all of the centimeters cancel out. And what we end up with is 1,500 times 1 times 1 times 1, all divided by 100 times 100 times 100. And what are the units? You have to do the same thing to the units that you're doing with the numbers. So what is meters times meters times meters? Your units are going to be meters cubed. So when you punch all that in, you're going to get 0.0015 meters cubed. Now, sig figs. How many sig figs does 1500 have? It has 2 sig figs, right? Trailing zeros at the end of a number are not significant unless there's a decimal point, and there's not. So you also need 2 sig figs for your answer. Now, one of the things I've noticed with students doing dimensional analysis is plugging into their calculator wrong. So please plug all this in and make sure you get 0.0015. Sometimes you need parentheses depending on the calculator you're using. A fail-safe method is to multiply everything in the numerator, write it down, then separately multiply everything in the denominator, write that down, and then do that calculation. But check your answers. If you haven't worked it out ahead of time on your own, make sure you check your answers, get the right one. All right, here is a you try. So this is where you're gonna hopefully turn off the video and do this yourself, and then come back, turn it on, and I'll work it out for you. All righty. So here's the conversion factor, which is totally defined. It's not going to take part in my sig fig. Meters has to go in the denominator, and I have to do that 3 times to cancel out the cubic meters. So it's kind of the opposite of what we just did on the last page. So your calculation is going to be 1.95 times 100 times 100 times 100. And just to kind of show you the mechanics, 1 times 1 times 1 in the bottom. All right. So let me see if I can do my mental math. Alrighty, so the given information had 3 sig figs, and so the answer has to have 3 sig figs, which it does. Feel free to express any answers in chemistry, either we call this decimal form or scientific notation. You should know how to go between scientific notation and decimal regular conventional form. So if you don't, you're going to have to review that because we are not going to take time to go through that. If you haven't discovered my YouTube channel already, there's hundreds of YouTube. So you can Google scientific notation if you need a reminder on how to do it, or just set your calculator in scientific notation. You should be able to go back and forth on your calculator with ease too. So let's see, 3, 6. Oh, I forgot units. You lose half credit if you forget units, so don't forget that. So the meters all cancel out, and I've got centimeters cubed are my current units. Alrighty, only a couple more slides. We're almost there. All right, there are going to be some problems. Again, I told you I'm trying to do a little bit more challenging problems to walk through with you too, so you don't get totally lost on your homework. What if you have dimensional analysis where you have to change the numerator and the denominator? So in this case, we have to go from meters to kilometers, and then we have to go from seconds to years. Do them one at a time. Don't try to do them at the same time, okay? You'll just get messed up. So let's go ahead and do meters to kilometers first. So our conversion factor, and these, just memorize those metric conversion factors, okay? The ones that I told you were important. There are 1,000 meters equals 1 kilometer. And again, that's a defined conversion. It doesn't factor into sig figs. So 1,000 is 10 to the third. Okay, that's where this is coming from. Make sure the meters are on the bottom. So what do we have? This is the speed of light. 3.00 times 10 to the 8 meters per second. I am going to ignore the seconds for this first set of calculations. So I want meters on the bottom. So 1,000 meters in 1 kilometer. The meters cancel. And so when I plug that into my calculator, I get 3.00 times 10 to the 5th. And what units am I left? Kilometers is on top and seconds is on the bottom. All right, so now we're going to convert the time, the denominator. So pay attention to that because it's a little bit different. So I'm going to write that answer, 3.0 times 10 to the 5th kilometers per second. And let's see, I need to convert seconds to years. Yeah, most people don't have that memorized. So we're going to have to go seconds to hours, hours to days, days to years. All right, so the first calculation, there are 3,600 seconds in an hour. Here's where I want you to pay attention. Since the unit seconds is in the denominator, in the conversion factor, it's got to be on the diagonal. So if you're converting denominator, the conversion factor unit has to go in the numerator. So 3,600 seconds. Seconds has to go on top, so it cancels in 1 hour. Okay. Now, you can do this, continue to do it one step at a time, or you can just do it one long run-on. So I'm going to do it one long run-on, but a lot of students like to do it one step at a time. So what do I have left for units now? I'm going to leave the kilometers alone, but the units in my denominator are now hours. So I now have to convert from hours to day. There are 24 hours in a day. Hours is still in the denominator, so hours has to go in the numerator, so it cancels. 24 hours in 1 day. All right, so now we have days is our unit, and we know there are 365 days in 1 year. All right, go through that, make sure you understand it, because that's going to be more like the type of problem you're likely to see on an exam. Here's one for you to try. So turn off the video, give it a shot, and then come back here and I'll work it out for you. Alrighty, let's see how you did. Here's the given information, and I always, if it's units in the numerator and denominator, I like to arrange them vertically. I converted the liters first, but you can do it in any order you want. So I know that units that I want to cancel have to be in the diagonal. And then I converted the milligrams. So milligrams is on top here, so I wanted it on bottom on the diagonal so that it cancels. And so what is the final calculation? It's 5,600,000 times 1, right? Divided by 1,000. All right, so now enter that in your calculator again, because the answer that you should get is going to be, let's see, 5.6 grams per milliliter. So if you enter it in your calculator and you get a much larger value than 5.6, it's just simply because you're entering it wrong. So you would put in 5 million, so how did I do that? Put in 5,600,000, okay, divided by 1,000, okay, and then you need to hit divided by again, or else put these in parentheses and multiply them. But regardless, you need to get 5.6 as your answer. If you don't, figure out how to use your calculator correct. Okay, so this problem is a challenge problem. So if you're feeling confident, or if you are up to doing a challenge, even if you bomb it temporarily, I want to challenge you to turn the video off and try this on your own. It is challenging. This is what I would call an A-level problem. So if somebody expects to get an A in my class, there are going to be some questions like this, not a lot, but some on the exam that you have to kind of think through. So it's good practicing them. Okie doke. I read the question a couple times. Like, I work everything on the fly because I don't want to have it all worked out for you, because I want you to see kind of my thought process. I don't know answers or how to work problems out right away. I just kind of think through them. But I wrote down everything first because this is kind of a confusing problem. So it said that the dose is 75 milligrams, and that's of the medicine. There are two weights they're talking about here, so I wanted to write what they were. So it says 75 milligrams of the medicine for every 1 kilogram of body weight. And that the medicine is a mixture in a container, and in that container there are 125 milligrams of the medicine per 1 milliliter. If there's not a number, it's assumed to be 1, right? So per 1 milliliter of medicine. So it's saying, how many milliliters of this medicine does a child who weighs 28 pounds? So the dosage is in terms of kilograms of body weight, and we have pounds. So the first thing that we want to do is figure out how many kilograms this child is. Alrighty. So change the arrow to a multiplication sign. Pounds cancel. So 28 times 0.454 is, I'm not gonna worry about sig figs to the end of this calculation. 12.712 kilograms. All right, so that is the body weight. And so now we have the body weight in kilograms. Now we have to figure out how many milligrams of the medicine, okay? And so that's our next conversion. So 12.712 kilograms of body weight. So we're gonna use this as a conversion factor. Kilograms goes on the bottom, so 1 kilogram down here. 75 milligrams goes on the top. Kilograms cancel. Now we've got 12.712 times 75. And that gives us 953.4. We've got milligrams of medicine, okay? Now that we have the milligrams of medicine required, we need to know how many milliliters we take out of this bottle to get this many milligrams. So milligrams has to be on the bottom, so 125 milligrams per 1 milliliter. Milligrams cancel. And now we end up with 953.4 divided by 125. And that gives us, I'm not paying attention to sig figs yet, 7.6272. The units I have left are milliliters. So this child needs 7.6272 milliliters of that medicine. Now let's pay attention to sig figs. So I'm going to tell you something that is going to make your life easier. Some conversion factors are defined like the metric conversions, and some are not. Some are estimated, but I'm just going to tell you right here, I don't want you to have to worry about counting sig figs in any conversion factor. All right, so don't pay attention to the conversion factors in your sig figs. Just pay attention to the given information. So the given information had only 2 sig figs, which means your answer can only have 2 sig figs. All right. So 7.6, do we need to round it? Look at the first drop number, it's less than 5, so no. So your final answer is 7.6 milliliters. If you got that right, I'm extremely proud of you. If you didn't, don't worry about it at all. That is a a really intense problem for this point. All right, real quick, 30 seconds more. Difference between precision and accuracy. All right, so precision is the reproducibility of a measurement. So it's how close together your values are. So let's say that you're measuring volume, and let's say you're using the graduated cylinder, okay? And you get 10.1, 10.2, 10.4. Let's say you do 3 measurements, okay? That's pretty good precision, okay? Let's say you try to use the beaker and then somebody checked the volumes. And in the beaker, let's say you got 9.4, 10.8, 9.9. So your precision is not as good if your equipment's not as good. So precision is reproducibility, or the range between your numbers. Accuracy is how close you are to the actual target value, okay? So my target value here was 10 milliliters, okay? So which one of these is more accurate, and how do I tell? And which one is more precise, and how do I tell? All right, so precision is the range, okay? Take the highest value and the lowest value, and that range, the larger the range, the lower your precision, okay? You want something with a really tight range to be precise. Accuracy, how close you are to the target, and you'll see in your lab, is usually represented with percent error. So it's a formula you'll get real familiar with in lab. So it's an absolute value, so there are no negative percent errors, okay? But you're gonna take the measured value, so let's say it was 10.3 milliliters, minus the real value, or the target value, and which would be 10, divided by the real, okay? And then times 100, and that gives you your percent error. This was a long introductory PowerPoint. Sorry about that. But that's it. We're done with this one.